Welcome everyone, and thank you for braving a snowstorm, or if you are watching the recording afterwards, well, thank you for joining from the comfort of your home. So today we are absolutely delighted to welcome Professor Tess Smidt from MIT. Professor Smidt is a physicist by training, got a bachelor's at MIT in physics, but already at that point, showed an immensely broad set of interests. If you ever visit MIT, you can see her cosmic ray chandelier on display, which scintillates when there's a cosmic ray hit. And also, another example of broad interests. Also has a minor in architecture. After undergrad, Professor Smidt went on to UC Berkeley, where she got her PhD, and then from there on became an Alvarez Prize postdoctoral fellow at Lawrence Berkeley Lab. Another honor that was bestowed upon her was she was named the Rising Star in Computational and Data Science by the Odin Institute at UT Austin. And last year she joined the faculty at MIT as a member of their Electrical Engineering and Computer Science department, where she is now the X-Window Consortium Career Development Assistant Professor. And she does all sorts of interesting work as part of her Atomic Architects group, where they develop really novel machine learning techniques that can be applied to physics, chemistry, material science, all sorts of things. And with that, I will leave it to you. So please welcome Professor Smidt to McGill.
Thank you so much, Adrian. Can I have you do all my introductions? I feel amazing right now. I'm so pumped. Thank you so much for coming. It's a pleasure to be here. This is actually my first time visiting another institute as a professor, so I'm super stoked that I'm here at McGill, getting to see all of you. I get to visit some friends from MIT undergrad days. And I'm really excited today to talk to you about some of the research I've been doing over the past few years. So I'm going to talk about unexpected lessons from neural networks that have symmetry built into them. And I'm going to do so without assuming that you know anything about neural networks or necessarily symmetry in the forms relevant to this discussion. For those that are either listening or for folks who like having slide links, I have a link to the slides. So it's just tinyurl.com/tess-mcgill-2022. So if you want any of the links to papers, you don't need to write them down. You can just go to the link here. And I'm going to focus on these two papers here. And I want to first point out my amazing co-authors, Mario Geiger and Ben Miller. Mario actually just started as a postdoc in my group, so super fun to have worked with Mario when we were both PhD students and postdocs, and for now him to be working with me. And Ben is currently a PhD student at University of Amsterdam. And a lot of the work, while I just moved to MIT in August, a lot of this work has been done at Berkeley National Lab thanks to the funding from CAMRA and the Department of Energy. And as far as any of the code that we're going to discuss today, you can find it all at e3nn.org. Last but not least, I have slides that can span the time, but I certainly don't need to finish my slides. I know what they say. So I love questions. So if you have any questions that come up, especially kind of in this wonderful setting, please feel free to ask. Okay, any questions? See? Okay, so first let's take it back a little bit and give you some context. So as a PhD student, I did a lot of quantum mechanical calculations. And so what I would do is I would take an atomic structure. So in this case, I'm showing the crystal structure for silicon. And I would use quantum theory and supercomputers to basically figure out where are the electrons. So this is the charge density for silicon. So where are the electrons? What are they doing? And might they do something useful that maybe we could use for photovoltaics, quantum computing, energy storage? And I just like to include this picture right here. So if you've never seen a supercomputer in the flesh, this is one row of cabinets of the Cori supercomputer at Lawrence Berkeley Lab. It's part of the NERSC supercomputing facility. And there's my dad and I for scale. So these are very huge computers. And so these calculations are very computationally intensive. They can take hours to days to weeks to months to years, especially if you put in very high fidelity settings. So these are very useful calculations, but they're very slow. And this is what I did sort of for my PhD. And I got to wondering, could we use machine learning to help us with the exploration of atomic systems such as molecules and materials? Could it help us speed up our calculations? So maybe we can do some calculations on the good old-fashioned way on the supercomputer, but could we do some of them kind of zoom? Could we do them faster and do larger scales and basically scan material space more effectively? Could we also hypothesize new structures? If I have a bag of structures and I throw them into the supercomputer, how do I think of new structures that I could then use for these calculations? Additionally, if I want to solve societal problems in energy and computation or even medicine, I have some properties that I would like my material to have. And can I actually make an algorithm that goes from properties to structures? So this is what I want. Here's a structure that'll give me that. And last but not least, can we use machine learning to actually develop a map that helps us map the structure of materials to its properties so that we can kind of better understand these more general trends in material systems? So this is what I wanted to do towards the end of my PhD going into my postdoc. And I ran into a few key challenges. One of it is, how do we actually go about representing molecular structures, crystals, or just any physical system to a machine learning method? How do you actually articulate that to the machine learning method? And how does this inform the assumptions that we want to build in to these methods? So these were two hurdles that we had to overcome. But another kind of topic that I want to focus on today are these unexpected lessons. So we were able to address these key challenges, but something surprising came up, which was, okay, what are the consequences of building these assumptions into our model? Will our model have properties that surprise or delight us? Any questions there? I'm actually going to grab my water because I know that I'm going to need it at some point, so I better do it now. All right, so how do we describe physical systems? Well, one sure way to do it is to use coordinate systems. We might use a coordinate system to describe where things are in 3D space. We might use a coordinate system to describe tensor properties, such as susceptibilities or forces, any sort of property that we might need to describe our physical systems in this case, 3D space. So suppose we have a system of molecules, and we have two different coordinate systems, 1 and 2. So these are different coordinate systems, but they're describing the same physical system. And we always have the option, since coordinate systems are figments of our imagination. We use them because they're useful to us, and they're useful for describing physical systems to things like computers. But there's no little coordinate system lying around, running around on the ground or anything. And so we always have the option to transform between our coordinate systems using the symmetries of, in this case, 3D space. 3D rotations, 3D translations, and inversion, which when you combine rotations and inversion, you get mirror planes. Here's the problem. If I were to show these two different descriptions to a traditional machine learning method, it thinks of them as completely separate systems. It's like, I don't know what you're talking about. These are completely different numbers. These are clearly not the same. How bad is this? Well, okay, so if I take an off-the-shelf traditional machine learning model, and it's not built to handle the symmetries of 3D space, I have to teach it about the fact that I want it to understand that this system of molecules is the same system of molecules, no matter how I choose my coordinate system. And for 3D data, this requires, or in general, this requires data augmentation. But for 3D, the amount you have to augment your data is pretty bad. It's at least a factor of 500. So let's say I want it to learn the patterns to recognize this little cube. So I want it to just be able to recognize this cube in any orientation or translation, inversion, anything like that. So if I'm training a model without symmetry, I have to actually show it at least like 500 different examples. There's also no guarantee that it actually understands that it's the same thing. It's just learning to mimic the fact that it's giving you the same output for these different inputs. And in physics, well, we really wanted to do things like learn things about quantum mechanics. It'd be nice if our model didn't have to learn about 3D rotations, which we actually understand very well. Any questions on that? Fantastic. Okay, so the problem is that traditional machine learning sees these as two complete different objects. So we want methods that see 1 and 2 as just different descriptions of the same physical system. So what we want is machine learning methods that have this symmetry built into them. So Euclidean neural networks are a class of networks that my colleagues and I invented a few years ago. And they have Euclidean symmetry built into them. And this means that, again, it sees a 3D system described by 2 coordinate system. It sees it meaning the same thing, even without training. So even if I haven't trained the model yet, it comes into the ether, it exists, I show it, the system described by these 2 coordinate systems, its output already will be the same modulo the coordinate system transformation. So this is a very strong inductive bias that's built into the very structure of the model. Okay, so what do you get by doing this? Well, let's look at some physical examples. So crystal structures, so we use these boxes, these unit cells. We have a box, we have atoms in the box, and then we tile the box in 3D space. So it's a compact description of an infinite system. And there's no unique way to describe a crystal structure. What I'm showing here is, again, the silicon crystal structure, and I'm showing a primitive unit cell, a conventional unit cell, and a supercell. Now they all differ, the box has different shapes, there's different numbers of atoms, and even worse than that, even if I say I want the smallest unit cell, well, there's even degenerate ways to describe that too. But the benefit of actually having models with Euclidean symmetry is that it understands that if I show any of these, so pick whichever representation is convenient for you, the model is guaranteed to give you outputs that mean the same thing. So if I input 4 atoms, it will give you predictions on 4 atoms. If you give it 10 atoms, I'll give it 10 atoms back. But the key thing is any atom that's actually secretly, symmetrically the same thing, it's guaranteed to have the same output. Question?
How do you implement the invariance?
I will get to that later in the slide. It's a great question, and it's not easy to answer. But I'm glad you're excited about it. OK. So yes, and I don't know if for the recording, the question was, how do we build in this equivariance? And so we're going to get to that later in the talk. This is just sort of priming you by what are the properties that you get if you build this in. OK, so let's say I'm interested in doing molecular dynamics. So I want to basically say, what are the forces that atoms feel when surrounded by other atoms? So if I have a molecule, and I have a rotated copy of that molecule, and I've built a model that can accurately predict the forces on one rotation of this molecule, it means that I'm guaranteed to predict the same forces on this rotated molecule, rotated appropriately. So the forces will rotate as I rotate the inputs. Additionally, molecules have many geometric motifs. There's different subgroups that you'll often see among different molecules. And the key thing is we're not just aware of the entire system, we're also sensitive to local patterns. And so these methods generalize very well to molecules that it hasn't seen, but have similar subgroups that it maybe has seen in training. And this is really useful for training molecular dynamics, or training models that can perform quantum mechanical accuracy molecular dynamics. And I'll mention that a little bit later. Questions on that? OK. And this is, again, reiterating the fact. So these networks can recognize equivalent geometric patterns in different orientations and locations, and it knows that it means the same thing. So in this rubidium manganese chloride crystal, we have the manganese atoms are octahedrally coordinated by these chlorine atoms, and they form these octahedra. And so it would be able to recognize that these different octahedra, these different local environments, are the same, just in different orientations. And the key thing here is that it doesn't have to see it in different orientations. Once it's seen one, it's seen them all. Here's kind of the first unexpected consequence that we weren't really expecting when we sought out to make a model that understood 3D rotations and translations and inversion. And the fact is that everything in the model ends up being a geometric tensor. So something that predictably transforms under rotation, translation, and inversion. Now, geometric tensors take many forms. You're probably familiar with scalars, so things that don't change under rotation, vectors, things that change with rotation. But geometric tensors are a very general data type. And things like the spherical harmonics, which are the angular portion of the hydrogenic atomic orbitals, and also useful functions in their own right for many things, these too transform as geometric tensors. In fact, each row of spherical harmonics, under rotation, they change into each other. So the key takeaway from this code over here is that these geometric tensors are fundamental data types in our neural network package. And so we can very specifically actually say, hey, I'm going to give you some input data, or I want some output data that acts like things like the atomic orbitals. So this ends up being really useful, especially when you're working with atomistic data. Questions on that? Cool. OK, so if we can represent things like at atomic orbitals, we can even represent complex tensors of atomic orbitals, which we use a lot of the time for describing material systems. So here's an example of a Hamiltonian for a molecule of water. So let me explain this picture a little bit more carefully. So on the right, we see a water molecule rotating. And we're like, OK, water molecule's rotating. The key thing is that the Hamiltonian that describes the interactions of the electrons between these different atomic orbitals, it's something that transforms predictably, but in a very complex manner under rotation. And the key thing here is I don't want a model that has to learn these complex transformations. And by building in this Euclidean symmetry, we don't have to. We can, again, train a model to produce this tensor. And it is able to get it just from one example. So explaining this a little bit more, the rows and columns of this matrix are atomic orbitals. And the matrix is describing the interactions between specific orbitals. So we have the oxygen orbitals, the hydrogen orbitals, and their interactions between. So this is just kind of a key takeaway is why it's really helpful to build this in and not make it so that the model has to learn these complex transformations. One more property, and then I'll explain the secret sauce behind how this actually works. So just like the properties of physical systems, the outputs of these Euclidean neural networks, which I'm abbreviating as E3 and N, have equal or higher symmetry than the inputs. And this is actually a very well-known phenomena that Pierre Curie probably wasn't the first to articulate, but at least wrote it down in 1894, and originally said this in French, but I don't speak French, so I'll say it in English, so my apologies. Is when effects show certain asymmetry, this asymmetry must be found in the causes that gave rise to them. Basically, the asymmetry doesn't just come out of nowhere. It has to be driven by some asymmetry in the system. So how does this manifest in something as seemingly unphysical as like a neural network? So this is what this graphic is striving to show. So the inputs, let's say I take 3 randomly initialized neural networks. So they've got parameters, it's all random, nothing's been trained. And I show it 2 different inputs. I show it the 3D coordinates of a tetrahedron, and I show it the 3D coordinates of an octahedron. These are very highly symmetric objects. They have the tetrahedral and octahedral point group, respectively. And what I'm going to do is I'm going to ask the model to output coefficients that I'm going to interpret as spherical harmonic coefficients. And then I'm going to plot that signal as a spatial signal, so just a linear combination of those, where I'm showing the magnitude of that signal on the sphere as the radius. So that's why we get these 3D shapes. So technically, you could show it on a sphere as having hot spots, but we're actually going to modify the radius. So this is an untrained model, but you can already see that the outputs of the model have equal or higher symmetry to the inputs. And so all these are high symmetry outputs. And again, this is just baked into the model because of our assumption of Euclidean symmetry. We'll play with this a little bit later to show what this can tell us about our data and whether it's actually abiding by our assumptions. OK, let's get down to the nitty-gritty details. Now that we have some sense of what these models can do and why we might care about them for modeling physical systems, how does this all work? OK, so first I need to explain to you what a neural network is. And we're going to do this in one slide. So neural networks are synonymous with deep learning. So deep learning is just the idea, I'm going to take a neural network, it has these things called layers, and I'm going to stack them on top of each other. Now, neural networks and deep learning are a specific paradigm of machine learning, which itself kind of is under the general subheading of artificial intelligence. We can abstract any machine learning model as some arbitrary function f that takes in some inputs x. This could be a description of our physical system, such as the geometry and features on that geometry. We have learnable parameters w that we're going to figure out, we're going to train using data. And then we have the predicted output y. Now, a key thing that we need to have for any machine learning model is we need to evaluate how well it's doing. So we need some sort of error or loss function. So one very popular example is the mean squared error loss. We take what we got, we subtract what we wanted, we square it, we take the average, and we say, OK, this is how you're doing, good or bad. The key thing about neural networks is that they're differentiable. And the reason why we need this is because this is actually how we update the weights. So we take our loss, and we just apply the chain rule. We take derivatives of the loss with respect to every single parameter in the model. And so this is why it's very common to use a special framework to train neural networks like TensorFlow or PyTorch or JAX, because they implement auto-differentiation under the hood so that all we have to do is say, OK, take the gradient. And so this is how we update the weights. Importantly, there's this eta parameter. So we don't just follow the gradient ad nauseum. We take a small step, and then we do this thing over and over again. So we'll keep showing examples, and we'll keep updating our weights. And then if people are interested, we don't have to do this now. But I also have a way to explain this with emojis. So feel free to ask for the emoji explanation at any point. But that's neural networks in one slide. Questions on that? OK. Oh.
Can you show us the emojis?
Yes, yes, thank you. OK, neural networks with emojis. OK, so we already talked about neural networks being a subset of machine learning and a subset of AI. And so we have a model, and the goal of that model is that it learns to give predictions based on examples. So let's do an example task of predict this animal's favorite treat. So I give it a chicken. It predicted that it wants to eat a chicken. This may be problematic. But what it really wants is it wants a grub. And so here is my model. I've randomly initialized my parameters. They're very confused and non-specific and sampled from a Gaussian distribution. That's what I would look like if I was sampled from a Gaussian distribution. And then we have our error function, so our judge, who's going to basically say, did we do a good or bad job? OK, well, you said chicken, and you were supposed to say grub, so you clearly didn't do very well. And so this is where the derivatives start coming in, because we need to now update the weights of our model using these derivatives. And so we have the calculus finger of blame saying, you parameter, you did a terrible job. You said that the chicken wanted chicken and it really wants this grub. You need to change in this direction. And the hope is that we then update the parameters. And eventually, it gives us the right description. It's saying, OK, the chicken wants the grub. Calculus is like, great. I have no further comments. And we repeat this again. So now we have a rabbit. And again, it predicts chicken. Also problematic. It wanted a carrot. Chicken is not equal to carrot. Calculus finger of blame is now saying, OK, you guys are not doing well. You guys need to change your ways so that we can predict carrots. We update the weights. The weights are all happy. The calculus thumb of approval is happy. And we continue our way. And so we just repeat this over and over until we've hopefully reached some convergence and gotten a model that is training at a level of accuracy that we're satisfied with. So that's my neural networks with emojis. So we can do this with the B. And then now we have a model which all of these parameters are, each doing something special and important, but they're all different. And now we have an actual trained model. Thanks for asking. Oops, no, hold on. I clicked the button twice. Okay. Bear with. Okay. So question.
Yeah, you're talking about changing the weights, but how do you change the entire architecture, like the number of layers and the number of nodes and things like that?
Yeah, and so, okay.
Could you please repeat the question?
Oh, absolutely. So the question is, okay, so we talked about changing the weights, but how do you change the architecture? So we tend to do this with what's called a hyperparameter search. And so we don't tend to use this with gradients, although there is a very active research area for doing architecture searches, for like figuring out what are best practices or what are general high-performing network architectures. So that is done, but it's done in a bit of a more brute force way. Although there are approaches for doing it in a more principled way. Thanks for the question. Any other questions? Perfect. Okay, so what does Euclidean neural networks bring to the table? How does it actually imbue itself with this symmetry? So it's really the combination of neural networks and something called representation theory, which comes up a lot in physics. So group representation theory is the math that describes how do things change when I operate on them. So how do things transform under what we'll say is group action? So we have some symmetry group, in this case the Euclidean group, so translations, rotations, inversion. And group action is simply we rotate something or we move it or we invert it. And it's the same branch of mathematics that brings us things like point groups, space groups, selection rules in spectroscopy, symmetry allowed and forbidden properties. It's also, of course, the branch of mathematics that is used to make arguments for certain parameters in the standard model, just different groups than what we're talking about today. So what representation theory tells us is that if we want our model to be aware of coordinate systems, but not biased by whichever coordinate system we choose, all of our neural network operations have to satisfy the following condition. So this is a condition. It's not a prescription for how to do it. It's saying the following condition has to be satisfied. I have my neural network function f. It has inputs x and w. If my function is indeed preserved symmetry, then I could either, for example, if G is an element of Euclidean symmetry, let's say it's a rotation, I have to be able to either rotate the inputs or rotate the output of the function. And it has to give me the same thing. So I have to be guaranteed that the group action commutes with my function f. So it's just different ways of saying the same thing. I have to be able to basically say, okay, I can rotate the inputs, rotate the outputs. This is the check. So all my neural network operations have to satisfy this condition. So this restricts what types of interactions we can have in our model. What are the rules of engagement for the different types of data in our neural network? So let me say a little bit about G and D of G. So G is like the Platonic ideal of, let's say, a 3D rotation. D of G is how we actually write that rotation down to act on the data type of x. If x is a scalar, D of G is just the identity, because scalars don't change into rotation. If x is a vector, then D of G takes the form as our familiar 3x3 rotation matrix. But what if x is a higher order tensor, like a matrix or a rank 3 tensor? Then D of G takes a different form. So this is important for reasons that I will go into more detail after. But the key thing here is that this is the condition that must be satisfied. Okay, so let's get a little bit more concrete. So what is actually the inputs to this network? So what we do is we give the model the geometry and the things that exist on that geometry. Now, this could be a 3D image. These could be a point cloud. It could be a graph. There's many different ways that you can represent geometry. But the key thing is that you're telling where things are in 3D space and what features live on those points in space. So let's take this example of 2-point masses. The types of features that live on those 2 coordinates in 3D space, we have masses. We have 2 vectors. We have, let's say, a velocity and an acceleration vector. And so these are different features that I might give to my model. The next key thing is that we have to actually tell the model what we're giving it. What are these numbers that you're throwing at me? What do they, what do they kind of mean? We need to categorize our features by how they behave under rotation and parity or inversion, 2 words for the same thing. For those that are familiar with group representation theory and irreducible representations, what we choose to do is we actually choose to encode all of our features as irreducible representations of O3, so the group of rotations and parity. If that doesn't mean anything to you, that is totally fine. But just for those in the audience for that whom that's relevant, just wanted to make that comment. So how do we actually tell the model what we're giving it? Well, we have to actually say, okay, the first number is a scalar. And so scalars don't change under rotation. So they have angular frequency 0. Furthermore, does a scalar change under inversion? No, it stays the same. What about a vector? Okay, well, I have 2 vectors. I have velocity and acceleration. Vectors have angular frequency 1. They change at the same rate as a change of basis if we rotate it. Does it flip under inversion? If I go x, y, z, minus x, minus y, minus z, so it does change sign. You can also have things like pseudoscalars and pseudovectors, which are very similar, but have opposite parity. So a pseudoscalar does flip under parity, and a pseudovector does not. So these are kind of to give you a feeling for the types of data and how we have to classify data inside our models. But the key thing to take away is that if we are demanding the network to be symmetry preserving, we first have to tell it, what did we give it? What symmetry exists in the system? What are the players, what are the features, and how do they transform? And then it'll take it from there. Questions on this?
So, do input data type and output data type must match?
They do not have to match. Oh, so the question, sorry, thank you. So the question is, do the input data type and the output data type have to match? And the answer is no, but they do need to be specified. So you do need to specify when you construct the network, what are you giving as input and what are you giving as output? And in fact, like here's an example. Let's say I give the model a crystal structure and I want to predict an elasticity tensor. An elasticity tensor, like a structure is just vectors in space and maybe some atom types, so scalars on those atoms. But an elasticity tensor is a rank 4 matrix. It has many higher order components. And so you could specify that you're inputting just the structure and the types of atoms, and what you want as output is an elasticity tensor.
Yeah.
Great, thank you for the question. Other questions? Okay, so those are the inputs, but how do we actually get to the good stuff? How do we actually learn complex descriptions of physical systems? So what we end up doing is we interact the features that we gave it with functions of the geometry. And one method for doing this is doing convolutions that, again, have Euclidean symmetry baked in. So let's first do a review of kind of standard image convolutions. So in a standard image convolution, the filter depends on your choice of coordinate system. Let's say I have this little filter. I'm going to scan it over my image. And it, in turn, basically I overlap the filter with the image, multiply it, sum, and that becomes a new pixel in my feature map, just like that. And then I would do this in a standard image network. I would just keep doing this with different features where these little filters are learned. OK, so what's different for us? I'm just checking the time. Great. When did we start?
Half an hour ago-ish.
Perfect. OK, great. Yes. OK, so that's what it is for images. Now, this is just a technical note that many of the examples I've been showing you are not images, they're actually points in 3D space. And so you can do convolutions over discrete domains like images or continuous domains like point clouds. And you can generalize this fully. The reason why we choose to use points instead of images when we're dealing with atomic systems is that images of atomic systems tend to either take up a lot of memory or they tend to be imprecise. You can see that some accuracy is lost if I try to make an image of this benzene molecule versus I can specify these coordinates with arbitrary precision that my computer will allow if I just use points. So instead of having this discretized filter that we're scanning over our image, what we actually end up having is we have a queryable function of space, W of R, where R is the relative distance vector between, let's say, an atom and some of its nearest neighbors, up to some cutoff, typically. And so basically I say, okay, here's my relative distance vector, plug it into W, I get some tensor back, and then I have to combine that with the features that exist already on that atom. So this is just describing the difference between performing a convolution operation on an image, a discrete domain, versus something like points. Okay, so in our case, again, we want Euclidean symmetry baked in. So this actually puts very specific constraints on our filter. And this will look very similar to those of you who have solved for the hydrogenic wave functions. So it turns out our filter actually has two separable components. We have a radial component, and this is actually where all the learned parameters live. And we have an angular component. And it turns out this angular component is actually fixed. It's the spherical harmonics, yet again. So what we end up having is a radial function that for a given L, we have multiple m's for spherical harmonics, so 2L plus 1 spherical harmonic functions. All of those angular functions will be paired up with the same radial function. So we're treating kind of that bank of spherical harmonics of the same L as one unit. So those numbers travel together. And all the learnable parameters actually go into this radial function, which we have ultimate flexibility in how we define. It can be a standard neural network that is applied to Bessel functions as a basis, or cosines or Gaussians. So we have a lot of flexibility for how we define and learn this radial function. But we must follow this prescription of having a filter function that's separable into radial and angular components. Furthermore, so these filters and our input are geometric tensor objects. So they're not just numbers. We can't just scalar multiply them. We might have a filter that transforms like a p orbital, which is like a vector, and we might have a input feature that's a vector. How do we multiply a vector times a vector? Well, we've got dot products, we've got cross products, we've got outer products. And so we have to use these generalized geometric tensor products in order to combine these features together. And that's kind of what I'm symbolizing right here, that the operation of sort of this tensor feature with this tensor feature is a mathematically well-defined operation that is specific to what we need in these neural networks. So for those of you who have taken Intro to Quantum Mechanics and you guys use Griffiths, you might recall this table of Clebsch-Gordon coefficients. And in fact, inside our network, we have Clebsch-Gordon coefficients to aid in this specialized multiplication of these tensor features. And so this is what's happening. We're not just doing scalar multiplication, we're actually doing the addition of angular momentum under the hood. Any questions on that? Take a break for water. Okay, so let's go back to this picture. I promised you that we'd come back to this example of, well, what's the significance of having neural networks who can only give outputs of equal or higher symmetry than the inputs? And again, this was just our case for a randomized model. But what about training tasks? Let's say we actually want to do something. How might this property manifest in a way that surprises us? So here I've got two tasks, seemingly simple tasks. Task one, I'm going to ask my neural network to deform this blue rectangle into this orange square. And task 2, where I'm going to do the opposite. I'm going to ask the neural network to deform this square into this rectangle. And we're going to see, can the network do it? Surely a powerful model should be able to do a task as simple as this. One quick thing, while I could have the network output vectors as the prediction, saying like, okay, as input I give you this geometry and maybe just a simple scalar of 1 on each of the atoms saying I'm an atom, I exist, or a point rather, and I exist. In this case, we're actually going to ask it to output a linear combination of spherical harmonics again. So we're going to see these blob signals. And the reason why I'm doing this will become clear shortly. But I just wanted to first notate that. So rather than outputting vectors, which we could do, we're actually going to output a spatial signal that might give us more information as to what's going on. So if we train the models, and we train it as far as we can, it gets perfect accuracy on the first task, and it's never able to do the second task. So it's able to go from rectangle to square, but it can't go from square to rectangle. And what you'll notice is, okay, so this blob perfectly aligns. The blue has a blob that overlaps with the orange. In this case, we have 2 lobes. What's going on? So this is the network telling me that I'm wrong. And this is the network telling me, okay, you asked me to distort this square into this rectangle. Which rectangle did you want? Because there's 2 of them. So there are symmetrically degenerate answers that me, when I first gave it this task, I didn't realize that it wouldn't be able to do this, or it was a related task. And I just realized that, I actually just broke my own assumption. See, a square is a higher symmetry object than a rectangle. And if I'm going from a square to a rectangle, there are 2 ways to do it. I can either make basically what's along the x-axis longer or what's along the y-axis longer. So this is basically telling us by inputting this prior of symmetry, our network will actually make sure that this principle is upheld in our training tasks, no matter what we might decide to throw at it.
Maybe you're going to get to this in the next slide, but can you handle systems with spontaneously broken symmetry?
Can we handle systems with spontaneously broken symmetry? I'm so glad you asked. In fact, this is going to come up, if not this slide, next slide, but the slide after. Okay. Let's talk about spontaneously breaking symmetry. So the way that we typically deal with this is that we might use something called an order parameter to basically articulate, we're going to break symmetry and we're going to break it in this direction. So suppose I have some energy landscape and I have a high symmetry state that's, it's at a local maximum. But if we roll downhill, we have 2 options. We have 2 lower symmetry spontaneous, or lower symmetry degenerate states. So with an order parameter, we can articulate, okay, I'm going to choose this one. We're going to go in this direction. So the next question is, okay, can we figure out the order parameter that allows us to bring our inputs and our outputs to be symmetrically compatible? And this is where the fact that we're using a neural network is really helpful. Remember how we talked about how we can always update the weights of a neural network by using these gradients? We can actually do that to change the inputs as well. So rather than just training the model, we're actually going to ask the model, okay, we're going to alternate between training the model and training our inputs. What is the minimal change in the inputs that I needed to tell you in order for you to be able to realize that I wanted this specific rectangle? And so if we do this procedure, and let's say we initially started off with just scalars. Scalars don't change under rotation, so they're basically are the same as the 0th spherical harmonic. And if we push these gradients through and retrain our model, we eventually find that the model learns an anisotropic contribution to these input parameters that is basically choosing either the x direction or the y direction. And importantly, it's only breaking what symmetry it needs to. You could imagine specifying a direction with a vector, but that's actually breaking more symmetry than you need. You really just need to specify like a double-headed ray saying this direction is special compared to this direction. And so what we find is that we get, in terms of these irreducible representations, any irrep of angular frequency greater than 2 with even parity. As long as we learn a little bit of those, that's sufficient to break this symmetry. So any questions on that? And so this was sort of like the most general question, like the most general order parameter that we could derive. But we can actually be a lot more strict. And I'll show that in some of the next slides. But the key insight here is, okay, we have a model. It will not allow us to break symmetry arbitrarily, but we can actually ask the model, okay, I understand that somehow these inputs and outputs are not symmetrically compatible. How do I fix it? And you can actually ask this question in a rigorous manner just by using the training procedure of the neural network. And I think that's really cool. Because normally the way you'd have to figure this out is you crack open your group theory tables and point group tables, and you have to actually figure out group theoretically, like what is the thing that needs to be broken. Okay, so what about maybe a more physical example? Where does this crop up? Well, it crops up in phase transitions, especially of crystal systems is where I'm most familiar with. So let's say we have a very high symmetry structure. This is a perovskite. And perovskites have a lot of really amazing electronic properties because these octahedra that compose the perovskite like to tilt. And they take some very complicated tilting parameters. Here's one that's a lower symmetry where we're getting a tilting along this particular plane. So let's say I wanted to train a model that's able to predict the distortion of perovskites, saying, okay, maybe under certain environmental conditions, I want you to learn that this perovskite is going to distort into this particular structure. Now, again, our model will protest and say, which distortion did you mean? There are 6 different versions of this distortion that are symmetrically identical. And there are different ways that we can articulate these distortions if we use the language of reciprocal space, as we often do when discussing phase transitions in condensed matter. We have particular reciprocal space vectors. But what we could actually do is we can, again, use this training procedure to recognize that, okay, there's actually 6 different symmetrically degenerate distortions that have this particular form. Any questions on that? Here's where it gets fun. So now that I'm basically articulating symmetry constraints as an optimization, I can start asking questions like, okay, I'm going to input this high symmetry structure, and I have this low symmetry structure, which has not only tilting in this plane, but it has tilting, tilting in this other plane. So it's more distorted than the one we were originally looking at. And I asked the question, okay, well, I want you to give me a structure that has some of the distortions of this one, but not all of them. I don't want any of the distortions that are in particular directions. Can you give me a structure of intermediate symmetry? And it turns out you can do this. So basically by just constraining which types of order parameters, which data types we're allowed to learn for these order parameters, I can actually restrict such that I can recover, again, a structure that has the same distortion in this plane, but not this one. Now, in order to do this the traditional way, again, I've got to break out my group theory tables. I have to look at it. I have to, do some calculations on rotations for geometry. So this is just another way at getting at kind of a familiar problem, but doing it through optimization, which I think is pretty fun. Okay, that was just highlighting the fact that we have an in-plane distortion in the target output versus the recovered output. Okay, so let's talk about maybe some open questions. I think we still, so we're still good on time. So how do we deal with correlated outputs? So in this example, each of these atoms is saying, well, half the time I go to one site, and half the time I go to the other site. Well, that's not really what we want. What we really wanted it to say is like half the time we all become this rectangle, and half the time we become this other rectangle. And the problem, as I stated it, having each atom sort of give its predictions, is actually it's not a powerful enough output for representing this problem. Because basically, we need them to be able to articulate that we all move together either this way or that way. And so how can we generally articulate neural network outputs that encode this correlation across multiple atoms? Because we don't want it to output things like, well, you know, one of us goes over here and one of us goes over here. We want to explicitly say, no, 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 this is not a valid configuration. We really want these two. So this is an open question for how to do this efficiently, effectively, for a variety of training tasks. And this is something that we're working on in my group. The primary application for this type of representation problem is actually in generative models. So atoms don't form random arrangements. They form recurring geometric patterns at many different length scales. And ideally, if we want to generate new atomic structures, we don't want to just lay down atoms one at a time. We actually kind of want to lay down these patterns. And what pattern I lay down over here will affect which pattern I lay down over here. So these outputs are correlated. So this dealing with kind of these data types that combine both spatial symmetries as well as permutation, kind of one of the more technical ways to describe it, is important for applications in generative modeling and the design of physical systems so that we can lay down patterns and articulate conditional probabilities for if I lay down pattern B, I'm only going to be able to lay down pattern C or D, but if I lay down pattern A, I have to lay down pattern F. So these are just some open questions, and I think it's just really fun to see how we can play with symmetry and neural network operations to get robust tools where we can actually rigorously articulate what we want to the model. So here's some takeaways. So Euclidean neural networks have Euclidean symmetry built in, and this makes them extremely data efficient. Something I didn't emphasize, but you don't have to show it very many examples for it to get the gist of what your physical system's doing. It makes them very generalizable. You can show it things that it didn't exactly see in the training data, but show it something that's kind of similar enough to it, and it does really well. Our unexpected features of these networks is that all inputs, outputs, and intermediate data are geometric tensors. And we have to interact these tensors with these geometric tensor products, things analogous to Clebsch-Gordon coefficients in the addition of angular momenta. So like physical systems, these networks cannot arbitrarily break symmetry. They preserve symmetry, so if you have some output that is asymmetric, it has to stem from the causes that gave rise to that. And last but not least, we can use these networks to uncover symmetry-implied missing data, even if the researcher doesn't know about it. So to wrap up, there's a bunch of things that I didn't talk about as far as applications of these networks. Essentially, we've done a lot of work lately for, I showed this diagram before of structures and properties and mapping things. So far, what we've done is a lot of the zoom part. So we've been making a lot of calculations go faster. So molecular dynamics, properties of phonons in crystals, Hamiltonians of molecules, and even asking rigorous scientific questions like how nearsighted are the electrons in water. And so I'm just going to leave this up in case any of these are of interest to you. And for more info on Euclidean neural networks more generally, you can go to e3nn.org. And please feel free to reach out to me at tsmit@mit.edu for any questions that we're unable to cover during this Q&A. And I'll take your questions.
Put up the website with the slides again, and you guys break it down.
Sure thing, happy to.
All right, well, thank you very much. And anyone have any questions? We'll go Robert, then Damien.
So the scale is distinct. So you don't have scale symmetry built in.
That's right. So I guess the question was in the microphone, but we don't have scale invariance, although you can also bake that in, but it would be a different symmetry to encode. So we are sensitive to scale because physical systems are sensitive to scale. I guess depending on your situation, there are certain cases certainly where they're not.
Okay, cool.
Thank you for the question.
Let's go to Damien next.
Hi, thank you. when you were showing how to decompose basically like the filters into, let's say, the radially symmetric parts and just the radial parts.
Yeah.
Does, let's say, the resolution at which you want your symmetry to be impose like a network size or a filter size, or?
Okay, so the question is back to looking at these filters, these radial functions and spherical harmonics, and basically asking, does the resolution sort of set the size of the filters? Am I interpreting the question correctly?
Yeah.
Yeah, so, okay, so in these functions, what level of spherical harmonic you go to is basically telling you your angular resolution. So if I have 2 points that are close together in terms of solid angle, I need a higher order spherical harmonic to differentiate, to be able to have 2 distinct peaks for those, for that signal. Now, the nice thing for atomic systems is that atoms do not like being next to each other. And so we can actually get away with a fairly low L. Majority of our models are under L equals 4, although for generative models, we have to go a bit higher just because of the nature of them. So you can actually stick with pretty low L for many applications. But what's nice is that, let's say you need higher and higher angular resolution, then it's very clear that you just add more and more spherical harmonics. So the basis has a very nice convergence property, much in the same way that for Fourier transforms of space, you add higher and higher order frequencies to get a better and better approximation. Does that answer your question?
Yeah, thank you.
Great, thank you.
Thank you very much for the very interesting talk. I have 2 questions, if you don't mind.
Yeah.
So the first question is that you gave us example of the crystal structure of silicon.
Yes.
And so I'm wondering, do you think your model can be applied to amorphous structure to particular properties?
I love this question. Okay, so the question is, we talked about crystal structures, but what about amorphous solids that don't admit a description in this nice compact unit cell? So the real answer is I don't know, but I suspect yes. So we haven't done this yet. There's so many different options for how you exchange information inside these neural networks. Do you only allow things close to each other able to exchange information? Do you allow long-range interactions? You can actually code this in when you're designing the neural network. All of this prescription is just telling you the nature of the interactions. When you interact 2 geometric tensors, you better use geometric tensor products. So it'd be really interesting to see what types of neural network architectures of this variety would be effective towards predicting amorphous solids. The other question I have is, do you have data? Because it'd be great to have data on amorphous materials, because it's certainly non-trivial to generate.
Yes. Okay. And actually, speaking of the architecture, that's related to my second question.
Yeah.
I'm very curious about the fact that you showed the output of the Euclidean neural network has higher symmetry than input. So I'm not a physicist, so I'm just wondering, where does the extra information come from? Does it come from the architecture of the neural network?
Yeah. Okay, so the question is, we said that the output can have equal or higher symmetry. So it's not necessarily higher, but it can be equal or higher. Where does that come from? And where it actually comes from is something called accidental symmetries. So depending on the particular situation, you can always have an accidental cancellation of certain contributions that lead to something looking like it's higher symmetry. And this happens in physical systems as well. But in these cases, it would be an accidental symmetry.
That's interesting. And sorry, just final comment that you asked us whether we have data. We do have data on two-dimensional amorphous carbon data. And then my advisor, Lena Smidt, was actually invited to give a talk here last semester. So we do have data on two-dimensional amorphous structure. So,
fantastic.
Yeah. So I think I'll reach out.
Yes, please do. Yeah, my email is just my first initial and last name at mit.edu.
Thank you.
So thank you for the questions.
We're gonna go all the way.
Make them run.
Yes, thank you for the very interesting talk. So I have 2 questions, if I may.
Yeah.
Yes, so first question, I'm wondering how your approach compares to approaches that only use scalars. So I guess what you're doing is more general, but some people have been arguing that scalars are enough.
Are all you need, yeah.
Yes,
I think that's
exactly.
the title of the paper.
So, yes.
Yeah. Okay, great question. I'm really glad you asked. Okay, so I talked about properties that change predictably under rotation. There's another approach that's even more strict than this, and it's saying we're only going to look at things that don't depend on coordinate system, scalars, so things like distances between atoms, angles between sets of 3 atoms. And there are several papers in the machine learning literature that are arguing all you need are scalars. Technically, that is true. But let me give a comparison. Let's go back to the elasticity tensor example. So an elasticity tensor, rank 4 tensor, so you would think it's 3 to the 4th, so 81 parameters. It's actually 21 because of symmetry constraints. If I wanted to be able to represent a elasticity tensor in terms of scalars, I need roughly, I think it's like 430 in order to be able to faithfully reconstruct that matrix. So it's true that you can just use scalars. However, we have a lot of evidence showing that you can learn much more effective and efficient and accurate models when you incorporate this geometric information, when you have things like vectors. And we're seeing this especially for molecular dynamics models. So what we can kind of do is that we can actually make our model only deal with scalars by just turning off the spherical harmonics, that we only have scalar spherical harmonics. And so we can actually do an ablation study. How does the performance suffer if we only deal with scalar information? And what we see is that it suffers actually significantly. So having vector-like information or traceless symmetric type information turns out to help a lot, especially as you go to higher order quantum mechanical calculations. So we've been able to show if you do like coupled cluster type molecular dynamics. And that's actually, let me put up the relevant folks. I want to make sure I'm showing off my amazing collaborators. Yes, so Simon, Albee, Boris, and friends. So what they've been able to show, or we've been able to show together, is that these higher order tensor features are really helpful for capturing the interactions of high quality ab initio data. Thank you for the question.
Let's make your second question the last one.
Yes. So do you think on the generative modeling side, equivariant or invariant normalizing flows could be interesting for what you're looking to do?
Okay, so the question is whether equivariant or invariant normalizing flows could be interesting for generative models. So kind of at a high level, what a normalizing flow is, typically when you're using these to generate new examples, you maybe like randomly initialize some initial structure. It could be random, or maybe it could be symmetric. So you're saying, okay, I know something I want with symmetry. Now change it into some other thing with the same symmetry that looks different. So I think those types of models are very interesting. I don't have extensive experience with them. And so I'm not sure if I'd be able to do kind of what I'd like with them, which is to make sort of these hierarchical models of atomic structures where you can represent these different geometric motifs and go in and tweak things. But it's certainly possible. I have a collaborator, Jonas Kohler, and he's really the person I always go to when I have questions about equivariant normalizing flows. So he's kind of my local expert. So it's a great question, and I don't really know.
Thank you so much.
Yeah, thank you for the question.
All right, thank you everyone, and let's thank Professor Smidt once more.
Thank you.